Hi, my name is Changho Hwang, a PhD student at KAIST. I'm going to present elastic resource sharing for distributed deep learning, which discusses an efficient multi-tenant cluster system for deep learning training workload. This work discusses a system that handles multi-tenant training workload efficiently. It is important because it is a very expensive workload. First of all, deep learning training, or DLT, is well known to be costly. According to a recent report, modern NLP models cost roughly $1 per 1,000 parameters training. Moreover, users of this system are often non-experts in distributed systems, thus these jobs often scale poorly and underutilize resources. The workload also runs many of such DLT jobs simultaneously. We need an efficient system to reduce the huge cost, which have several design goals like reducing average job completion time, handling job fairness, and increasing resource utilization. In this work, we investigate efficient resource sharing for DLT jobs. Resource sharing algorithm is the key to efficient cluster usage. The figure illustrates an example of a working system. Each tenant defines a DLT job and submits it to the GPU cluster, and then the resource manager assigns GPUs to each job. There are two kinds of resource sharing, non-elastic versus elastic sharing, which I'm going to explain in the following slides. Non-elastic sharing refers to the scheme that does not redistribute the assigned resources once they are allocated to a job. Due to its simplicity, it is very popular and commonly employed by the existing systems. Under this regime, each job declares and requests its own resource share, and the system only determines whether to admit the request or not. Therefore, we call this job-level coarse-grained scheduling. The figure shows that job A arrives earlier than job B, and it is admitted to use 4 GPUs, which leave 4 GPUs idle in the cluster. When job B arrives and asks for 8 GPUs, its request is rejected due to lack of resources. In contrast, elastic sharing, which is the focus of our work, can aggressively redistribute the assigned resources to better utilize them. That is, the system autonomously determines the share of every job, so we call it resource-level fine-grained scheduling. The figure shows that each tenant submits a job without a resource request, since it is determined by the resource sharing algorithm based on the system-side analysis on each job. This fine-grained resource allocation scheme presents us great potential for cluster-wide optimization, but realizing the benefit is challenging in practice, both in terms of algorithms and systems. Our work contributes to both algorithms and systems to support elastic resource sharing of DLT jobs. On the algorithm side, we design Apathetic Future Share algorithm that leverages elastic resource sharing for reducing average JCT. On the system side, we design CoDDL resource management system optimized for elastic resource sharing. First, I'm going to explain the algorithm side challenge and our design. Reducing average job completion time may sound trivial because it is studied for decades and now we learn it from textbooks. It is well known that prioritizing short jobs reduces average JCT, as shown in this quote from the operating system textbook that says, shortest job first is provably optimal for minimizing average waiting time, which is equivalent to average JCT. So it may be natural to employ shortest remaining time first, or SRTF. Unfortunately, SRTF is often suboptimal for DLT jobs, so SRTF is not enough. Actually, SRTF is optimal only when every job throughput scales linearly to the allocated resources. For example, what if there is a long job whose throughput scales very well and a short job whose throughput rarely scales? This figure shows an example. The long job A scales linearly to the number of GPUs, while the short job B does not gain any additional throughput beyond 1 GPU. Which job do you need to allocate more GPUs to reduce the average completion time? This is an obvious case. You should give more GPUs to job A even if job B is shorter. Then it'll decrease the JCT of job A and thus reduce average JCT. More generally, what if the scalability of the short job is somewhere between non-scaling and linear scaling, like the figure on the right side? Furthermore, what if the long job also does not scale linearly? This is a non-trivial problem, and this is the key problem we tackle in this work. Unfortunately, this is a common situation in DLT jobs. Their throughputs are known to scale sublinearly due to the inter-GPU communication overhead in distributed training. From the previous discussion, we have shown that resource efficiency also matters in reducing average JCT. When I say resource efficiency, I mean the fractional throughput gain when a job uses more resources. This figure shows that none of existing algorithms have explicitly handled both shortness and efficiency at the same time. Therefore, we come up with proposing our own algorithm named AFS that handles both of them explicitly. AFS is an elastic resource sharing algorithm to strike a balance between prioritizing shortness and efficiency. The algorithm is based on our equation that determines when efficiency or shortness wins. But due to the time constraint, I'll only briefly explain the meaning of this metric. At first, this metric does not bias into either shortness or efficiency. Say, a churn event happens, which results in lighter resource contention, then it biases towards prioritizing short jobs, and if the churn event aggravates resource contention, it biases towards efficient jobs. More analysis is in our paper, so please check it out. We derived two variant algorithms out of AFS. The first one is AFSL, which leverages the exact remaining time of jobs like SRTF. We present this for apple-to-apple comparison against SRTF, but like SRTF, AFSL is unusable when we cannot calculate the exact remaining time of jobs. We compare AFSL against existing schedulers that also leverage the exact remaining times. We simulated schedulers using real-world cluster traces and measured their average JCT reduction rate compared to the one of SRTF. The figure shows that AFSL outperforms all existing schedulers in all traces, showing up to 2.67 times of improvement over SRTF. It achieves the high performance because it conducts fine-grained resource sharing to carefully balance between prioritizing shortness and efficiency. We also present AFSP that does not leverage the job length information. Like variations of SRTF, AFSP leverages processor sharing to achieve this. This may degrade the scheduling performance, but it is more practical than AFSL. We compare AFSP against existing schedulers that do not leverage the job length. The figure shows that AFSP also outperforms all existing schedulers, achieving up to 3.11 times of improvement over Tiresias-L. The details of AFSL and AFSP algorithms are found in our paper. Now let me move on to our system size challenges and design. Despite the algorithmic benefits, elastic resource sharing performs poorly over existing systems. This is because it frequently reconfigures jobs for the share readjustment. In our traces, the reconfiguration happens 6.3 times on average and even up to 22 times more than non-elastic sharing algorithms. This often drops cluster utilization significantly due to severe thrashing on a burst of reconfigurations. To show the thrashing issue, we replay a full-scaled trace in our 64 GPU cluster. The system follows existing design and runs AFSP scheduler. During the execution, we monitor a single job that is submitted at time 0. The first figure shows that new jobs are dynamically coming into the cluster, and the second figure shows that the scheduler is changing the GPU share of the monitoring job. In the last figure, we can find that the monitoring job progress is slowed down whenever its GPU share changes. As you can see, the progress is significantly slowed down, especially when many jobs are submitted frequently to the cluster. This is because the system is busy reconfiguring the monitoring job and the job cannot progress during the reconfiguration. To tackle this issue, we present our resource management system named CoDDL. CoDDL front-end accepts user-written DL models and submits them to the backend, and the backend runs the scheduler in the centralized controller to determine or readjust GPU shares for each model training. It automatically scales each model to adapt to the readjusted share. CoDO backend is designed to minimize the reconfiguration overhead. It presents two key designs. The first one is concurrent reconfiguration with job execution. This design allows each job to keep training even while a part of its GPU workers are under reconfiguration. The second one is fast canceling stale configuration commands. We observed that on a burst of reconfiguration, many stale configuration commands are incurred across the cluster, and we need to cancel these as soon as possible to mitigate unnecessary reconfigurations. This presentation omits other system details in the paper, including failure handling, GPU placement, job throughput measurement, etc. System optimizations of CoDO hugely relax the thrashing issue. When we run the same experiment to compare CoDO with the legacy system implementation, it reduces JCT of the monitoring job by 2.7 times. Our paper also presents average JCT evaluation over CoDO. To summarize, we have investigated elastic resource sharing for multi-tenant DLT jobs, and we have shown that it enables significant improvement of scheduling performance. To be specific, we have presented an elastic resource sharing algorithm named AFS. We have shown that it reduces average JCT by a balanced prioritization of short jobs and efficient jobs, achieving up to 2.67 times and 3.11 times improvement over SRTF and Tiresias-L respectively. We also present CoDL, an optimized system for elastic resource sharing. It realizes the algorithmic benefits of the elastic sharing algorithms by mitigating cluster thrashing via its efficient job reconfiguration. That is the end of this talk, and thanks for listening.